Greetings, friends. My name is John Gabriel, and this is the New Calculus channel. So, today I'm going to talk about something that many mainstream academics haven't even imagined, but which, of course, forms a basis for integration in the New Calculus. Actually, to be quite frank, the method I'm about to show you is, in fact, called natural integration. Okay, so, and I'm going to explain to you how it works. And it's very easy. And like I've told you before, a definite integral is really nothing more than an arithmetic mean, the product of two arithmetic means. Okay, so let's see how easy it is. Let's begin. Now, so imagine that we want to solve the area under this curve between these two, or find the area under this curve between these two pink lines. We don't have to do anything with Riemann sums. That's just a bunch of garbage. We don't have to use limits or anything like that. This area here is in fact a product of two arithmetic means. Now, natural integration is what happens if we take the mean of these two, which supposedly is just the middle value. Obviously, it's not the mean, but it's the middle value, okay? And if we just use this mean and multiply it by the interval, which is also an arithmetic mean, then what we have is this area here, 0.93, which is not quite correct. But we can always add more. So let's show the partitions as well. We can always add more. Okay, so two means. And if we take these two means, then we get a better mean and we get a better area, right? So as we take more and more values for n, then what happens is that we get closer and closer to the real area, okay? 0.93. So, yeah. Now, I haven't actually calculated this area exactly by looking at the primitive function, which is x cubed. So all you'd have to do is subtract this little distance here from this distance, and you'd have the area, which is 0.279. That's according to the mean value theorem, which many don't understand came before the fundamental theorem of calculus. In fact, the fundamental theorem of calculus is derived in one step from the mean value theorem. So this is natural integration. All you're doing is you're systematically taking means of an equal number of partitions. And obviously, the more partitions you take, the better the representation of the area. And you can do that with any curve. By the way, you can even try it with a curve as complex as the Gaussian curve, or the one that you use for normal distribution, and you'll see that this works incredibly well, by the way. And all you're doing is you're finding the arithmetic mean of all these red lines, and as you get, bigger and bigger, what happens is the arithmetic mean becomes more accurate. Okay, now I don't know if this is going to work because it might run out of memory space, but look at that. Okay, so it seems that 0.93 is reasonably accurate. Okay, so 0.93 is the arithmetic mean of all the ordinates under this curve here, and it seems about right, because it would be from a horizontal line through this point here, like that. Okay, and all we're doing is taking this little chunk here and putting it down here to form a quadrangle, not a quadrangle, a quadrilateral, and thus we are able to use the general formula for area, which is the product of two arithmetic means. So I will let you have a link to this applet so that you can play with it. You can even change the function. If you go down here, you can, I don't want to do that. Oops, I just want to move this out of the way. Come on, let me see. Oh, seems like I can't do that. What if I try to put it in there? Well, I'll tell you what, you can do it in your own time, but you can actually type in this bar at the bottom here, you can say f of x, f dash of x. By the way, there's a good reason I've called it f dash of x, because when you talk about the mean value theorem, it's f prime of c, and there's obviously one of these here that is going to be equal to the difference of these two ordinates. That's all it means. Okay, so if you know how to do subtraction and you understand why the mean value theorem works, and you can do that if you download my free ebook, it's a piece of cake. All it is a telescoping sum. Then you know how to do integration. And that's all that integration is. And by the way, this extends into everything. It extends into vector calculus, multivariate calculus, and it's the same regardless of what you want to do. So this is what I call natural integration. Just break the interval that you want to find the area into a reasonable number of, sufficiently reasonable number of intervals so that you can take the mean of those. Now remember, you don't need to do this if you know what the primitive function is, right? So in this case, we know what the primitive function is, cube, so we don't have to do any of that. But in many cases, it's not easy to find the primitive function, even though the new calculus has a method to systematically integrate any function. And of course, that function must be smooth, meaning it is continuous and smooth. Has a tangent at every point in a given interval, and only one tangent, and the tangent doesn't cross the curve at the point of tangency. That's the original definition of tangent. Very well. I can't think of anything else right now. I think I've talked about this before, but I'm going to let you think about that. You can ask me questions in the comment section, one question at most at a time, and I'll try to answer. Hope you've enjoyed this little presentation on natural integration, and this is a new calculus channel. Till next time, I'm John Gabriel. Goodbye.